Let us discuss an example of a thin walled channel to make the concept of shear center more clear. So, we are given a thin walled channel section having dimensions shown in the figure. In other words, we have a channel having depth h, width of the flange b, and thickness of the flange and the web equal to t. We are asked to locate the shear center of this channel. So the first step in such type of question would be to determine the moment of inertia. As we know, the shear stress equation is VQ over IB, where V is the applied shear, Q is the first moment of area, I is the moment of inertia of the whole cross section, and B is the width of the component under consideration. So in the case of this channel, we can determine the moment of inertia about the neutral axis equal to T h cubed by 12 plus 2 times big bracket bt small bracket h by 2 square big bracket close. In other words, we consider each of the component, namely the flanges and the web, as a thin-walled structure. So the moment of inertia of the web is th cubed by 12, and the moment of inertia of the flanges is taken as 2 times area into the square of distance of the flanges from the neutral axis. Thus, we will get th square by 2 small bracket h by 6 plus b. We have discussed the concept of shear flow, which is equal to VQ over I. In other words, B can be taken to the right hand side, and the tau multiplied by B gives us the shear flow. So we are left with the equation VQ over I. Now, I is the moment of inertia of the whole cross section, V is the applied shear, and Q is the first moment of area corresponding to the component under consideration. So in other words, if we have a channel section having, for example, 100 millimeter wide flanges and 250 millimeter deep web, we can work out our moment of inertia of the whole cross section. And for the first moment of area, we can divide the whole cross section into components AB, BC, CD, and DE. Now, the first moment of area of the flange AB would be equal to the area of the flange, which will be 100 millimeter times 2.5 thickness times the distance between the neutral axis and the center of the flange, which will be 125 millimeter, since the distance between the center of two opposite flanges is 250 millimeter. Thus, we will get QB to get the shear flow in component BC. We will have to add the influence of shear in component AB and the component BC. Therefore, the shear flow at point C would be equal to the first moment of area of AB and the first moment of area of BC. VQAB by I is already worked out, and we have to determine QBC, which will be then added to AB, and correspondingly we will get the shear flow at point C. So VQBC by I will be equal to the area of this of the web, which is 125 millimeter times the thickness, 2.5 millimeter, and then 125 by 2, which is the lever arm as given over here. So area times the lever arm is our first moment of area of DC. Adding up, we will get 9175 Newton per meter. Since the cross section is symmetrical about the horizontal axis, hence QD will be equal to QB, and the shear flow in DE will be equal to AB. From the shear flow, we can easily determine the shear forces in the component AB, BD, and DE. In the case of AB, we can multiply the shear flow with the length or with the width of AB, which is 100 millimeter, and we would get 282 Newton. In the case of web, we have to determine the average shear flow. Now, we have already worked out the shear flow at point C, which is 9175. Now, the average shear flow in the component BD will be equal to QB 5646 plus the average shear flow in BD. So the average shear flow will be equal to 5646 plus 2 by 3 of 3529. Remembering that the shear flow in BD is actually parabolic and 2 by 3 is the average of parabola. So 5646 is a continuous shear flow in BD, and 2 by 3 of 3529 is actually the average exercise, and we can repeat and determine H is equal to 282 Newton. So coming back to our example where we are given the width of the flange as B and depth of the web as H, we can use the same process. First of all, determine the moment of inertia, then work out the shear flow in the flange, after that in the web, and then in the flange again. In order to determine the forces, we can multiply that with the corresponding length of the component and get the forces over there. Since the channel section is not symmetrical about the vertical axis, therefore it has got a tendency to rotate. Hence, to stop that rotation, we apply a force P at a distance E from the center of the web. Hence, V time E will be equal to the flange force times H, and the flange force is determined as VB square divided by 2H big bracket H by 6 plus B. So plugging the values, we will get the eccentricity E, which is equal to B square by big bracket H by 3 plus 2B big bracket close. So the flange force, as we discussed, is determined by multiplying the shear flow in the flange with the distance dx. Dx is a width of an element chosen at a distance x from a certain reference point. Q, as we said, is determined by using the formula VQ or I. So plugging the value in this integral, we will get flange force equal to VB square divided by 2H big bracket H by 6 plus B.